During the war, the Japanese cut off the supply of quinine, and the troops were fighting in the Pacific, and malaria was very prevalent there, and they needed antimalarials. They asked Shannon, who was a physiologist, a renal physiologist working on way, to head a program to clinically test the synthetic antimalarials at Goldwater. Shannon had a good nose for picking people. Young people, instead of fighting the Pacific, they worked on antimalarials. And it was so important to have a milieu where there's a lot of bright young people who were doing good work, and it had a great influence in my thinking. After 4 years of working at Goldwater, I knew I didn't have a chance for an academic appointment without a PhD. I didn't have it. I had no inclination. And then I saw an advertisement in the New York Times where Shannon was appointed the director of the intramural program for the Heart Institute in Bethesda. And I wrote to him, and he hired me. And he also recruited a remarkable group of people. It was in Building 3. 3 people ultimately became Nobel Prize winners. There's Kornberg, Anderson, myself. 20 of them became members of the National Academy. And I became interested in a group of compounds, the sympathomimeticamines, the amphetamine, ephedrine. They interested me for several reasons. First, they affected behavior, and they raised blood pressure. I became very curious why the body can metabolize drugs, chemicals I never saw before. And this, of course, occupied the minds of biochemists and pharmacologists for 100 years. I thought I'd like to tackle that problem. The man who occupied the bench next to mine, Gordy Tompkins, he was a postdoc then with Brody. He's a brilliant man. He says, Julie, best way to study, try to find out, why don't you find out what enzyme? I told him I had no experience in enzymology. He said, all you needed was a liver and a razor blade. Used to work making slices in those days. Studied metabolism. 1956, Seymour Ketty, Ed stepped down from the directorship, became the head of this laboratory of clinical science. We had seminars every week, and one seminar he had a report from a group of 2 Canadian psychiatrists who found when they left adrenaline in the air, it turned pink. And they took it, they claimed that they started to hallucinate. Schizophrenia possibly would be caused by an abnormal metabolism of adrenaline. I was fascinated by this report, and I looked through the literature. I found there was nothing known about what happened to adrenaline, except there was an enzyme that deaminated it, monoamine oxidase. I said, well, I might as well work on the metabolism of adrenaline, since it is so closely related in structure to amphetamine. First, I tried to look for the enzyme that converted adrenaline to adrenochrome. I couldn't find that enzyme. I spent 4 frustrating months. Well, one day, I saw the abstracts of the Federated Societies, Macmillan and Armstrong, showing that patients with pheochromocytoma excreted a lot of a compound called vanillomandelic acid, which is a methylated compound. And looking at the structure, I knew it must be coming from adrenaline or noradrenaline. I suspected that would be formed by first the methylation of adrenaline or noradrenaline, and then the deamination by monoamine oxidase. And I thought the methyl donor would be S-adenosylmethionine. And I found when I added all those ingredients together with adrenaline, it just disappeared, metabolized. But when I left one of them out, it stopped. So I knew I had an enzyme there which transferred the methyl group from adrenaline to the one of the hydroxy groups of adrenaline. We called it epinephrine. One thing I used to do when I worked with on drug metabolism, study the tissue distribution of adrenaline, labeled adrenaline, tritium labeled. And we found it was distributed in various tissues, but it persisted in many tissues. This is unchanged long after the physiological actions were hours, it was staying. So it was sequestered someplace. And I realized that it was in the spleen and the heart, which contained a lot of sympathetic nerves, highest concentration. So we suspected it must have been sequestered in sympathetic nerves. And that was an important...
That was a revolution.
At that time, I was attracting postdocs. One was George Herting, classical Viennese pharmacologist. We were discussing this problem, how we can prove it. And he came up with a brilliant idea. He said, what you can do is just take out the superior cervical ganglia, just unilaterally. When you do that, nerves would generate just on one side. So you would have a unilaterally denervated animal, a cat. When we injected radioactive noradrenaline, the radioactivity was localized only on the innervated side, so we knew it was going into the nerves. But we realized we had something very important. One experiment we did was perfuse it. We perfused the spleen, and when we stimulated the spleen, there was a release of noradrenaline. Not only was it taken up, but also released. Then we call this process reuptake. What we did was injected radioactive noradrenaline, and I happened to be working on the pineal then. Pineal was very rich in sympathetic nerves, noradrenergic nerves. I thought, well, it'll take a long time before films the radio. It'll take weeks. I was very impatient. Let's try it after 2 days. And there it was. All the radioactivity was in the sympathetic nerves. Not only that, it was always localized over dense core granules. These are little vesicles. We suspected that this was the storage for the noradrenaline. So we knew we had it. We also did the distribution with the wild-mouth herb. He was a German biochemist who actually did a lot of work on biochemistry of mental illness while he was in England, because he had to leave Germany during the Nazi regime. And we developed methods for measuring adrenaline. He developed very nice methods. Let's measure the effect of drugs on the uptake. We couldn't do it in the brain at that time because it didn't cross the blood-brain barrier.
Yeah.
First thing I did is try cocaine, and found when we gave cocaine, it blocked the uptake in tissues. We found, for example, in the heart and the spleen. When an animal was treated with cocaine, it was much reduced radioactive noradrenaline, so we knew cocaine was blocking it probably into the nerves. And we tried a whole bunch of drugs. Amphetamine did the same thing. Later on, my postdocs found that not only was the antidepressants blocked reuptake of noradrenaline, but Joe Coyle, who was a postdoc, found it blocked the uptake of dopamine. Sal Snyder found the antidepressants blocked the uptake of serotonin. And of course, they used simplest methods, they used slices. And of course, this is how the whole Prozac story, and all of the antidepressants were made. Using the simple method, they can screen thousands of these synthetic drugs rather than giving it to humans. These postdocs came, they were so bright to begin with. When they came to my lab, I realized that most of them were much smarter than I could never have gone to Harvard Medical School or Hopkins or wherever they went. Never could have. They were very bright. They picked up things fast. They developed things. But I think the interaction with their good brains and their smartness and my ability to think, see connections, I think made a good combination. And also, I think, I didn't try to treat postdocs as another pair of hands for my work. I treated them as people who were curious, who I tried to direct them, pick a problem that we were both interested in, and get them enthusiastic enough so that, and also that they succeeded initially so that they can go off on their own, which they did. The greatest thing that happened to me in research was working with Brody. The second greatest thing was leaving Brody.